All right, I think we're going to get started, folks. A few awards. We've shifted from the awards banquet to now Tuesday afternoon before the Nikolsky lecture.
Okay, I have the distinct pleasure of introducing the Robert Lichten Award winner. It's given to an author of a technical paper who has not previously presented the results of his or her work at a technical conference. I believe that's at the national or international level. And the winner this year is Angela Baccio of Bell Textron. Angela, please come forward. Angela's paper is titled Modeling Unsteady Aerodynamics in RCAS, Army Program, for high-speed rotor aeroelastic applications, and she will be presenting her paper tomorrow afternoon at the Dynamics Technical Session. It's the last paper of the day. Angela, we're very pleased to recognize you with the Robert L. Lichten Award. And at this point, I'd like to turn the podium back over to Angelo Collins.
I think most of you are familiar with the Vertical Flight Foundation. We've given over $1 million in scholarships to students over the past few decades. Bill Warmbrodt from NASA was our first recipient, of course. This year we were able to give $126,000 through the VFF. We were able to add through that another 4 scholarships. So we're just thrilled to be able to continue this wonderful foundation scholarship program. Our most recent fully endowed scholarship is on behalf of Mark and Lynn STOL. They're the parents of Alex STOL, who tragically passed away just 2 years ago. He was a Joby engineer, one of the founders, and a proud member of the Vertical Flight Society. This new scholarship in his name is $5,000, and it will be given to a student that is pursuing a study in sustainable aviation. And so the recipient this year is Taemin Jong from Seoul National University. He's also on our student council. So I'm going to ask the STOL family and Taemin to come up on stage to take a picture. So thank you, guys. I'm going to hand the podium off to Mahendra Bhagwat. He's the chair. He was our former technical chair, but now he is the chair of the VFF Scholarship Committee, and he'll be presenting this year's Vertical Flight Society Award. So Mahendra, come on up.
Good afternoon. So every year, the Society's Vertical Flight Foundation awards merit-based scholarships to students entering or already immersed in rotorcraft education. So first of all, I would like to begin by thanking the Scholarship Selection Committee. They had an incredibly difficult task of choosing just a small number of students from a really big pool of highly qualified candidates. The committee includes Tony Gardner from DLR, the German Aerospace Center, John McKeown, retired from US Naval Air Systems Command, Rajneesh Singh from the Army's DevCom Army Research Lab, Cliff Smith, Sikorsky, a Lockheed Martin Company, and he's probably producing this show here today. I served as the chair of the committee, the easiest job, but I also want to thank Julie Gibbs at the PFS headquarters and Jeff Sensei at the Army's Aviation and Missile Center, who helped with data analysis and keeping all the applications together. So as Angelo mentioned, this year the Vertical Flight Society is awarding 33 VFF scholarships in 3 categories, totaling $126,000. This is an increase of 4 scholarships and $6,000 compared to last year. And these students are going to be the future leaders of vertical flight. So give them a big round of applause. So now we are going to read the list of student winners, and I'm going to channel the voice of Rex Alexander to do that.
Thank you very much, sir. Now, as I call your names, I ask the recipients here today to step forward to the stage And remember to please stay on stage as we will be taking a photo once all the names have been called and you are all up here. As I announce the recipients, please hold your applause until the last awardee is announced so all the names can be heard. For the bachelor's degree scholars in alphabetical order, they are Sarah Kate Dockery, Mississippi State University; Molly Dolan, Oklahoma State University; Alex Duffy, Pennsylvania State University; Michaela Gaylor, Arizona State University; Caden Perry, Georgia Institute of Technology; Stefan Schmidt Justin, University of Twente; Emerson Self, University of Oklahoma; Ritwit Shankar, Indian Institute of Technology, Kanpur; Alexander Sickman, Texas A&M University. Master's degree scholars in alphabetical order are Kumar Dip Basak, University of Maryland; Heather Beers, Georgia Institute of Technology; Ron Berlin, University of Maryland; Corey Chi Anello, Georgia Institute of Technology; John Gillespie, North Carolina State University; Taemin Zhong, Seoul National University; Grace Nicole Johnson, University of Maryland; Sahil Nitin Kali, Indian Institute of Technology, Bombay; Ireland McClay, Georgia Institute of Technology; Mikhail Morcus, University of Maryland; Isabel Sands, Georgia Institute of Technology; Gray Simons, Georgia Institute of Technology; Vinesh Upur, University of Maryland; Kunal Rahal Yadav, University of Texas at Austin. The doctorate degree scholars in alphabetical order are Daniele Granata, Politica di Milano; Huan Lee, Georgia Institute of Technology; Se Andres Fataha Massoum, University of Toronto; Nathan O'Brien, University of Maryland; Junwei Park, Seoul National University; Joel Raka Proval, Pennsylvania University; Pranav Sridhar, Georgia Institute of Technology; Vivek Vital Upur, University of Maryland; Zoel Wong, Georgia Institute of Technology; and Danielle Yu, University of Texas at Austin. Please give a round of applause for all our participants. All right, bear with us as we get our group photo. Congratulations to all the recipients. Job well done. With that, I'd like to call Angelo back to the microphone.
As Mahendra said, we're going to need a bigger stage if we're awarding all these scholarships. It's really exciting. So we have a new scholarship. It's called the Executive Director Scholarship Award. And it's to acknowledge a student that has demonstrated unwavering dedication and fearless commitment through their volunteer efforts in support to the Vertical Flight Society. This year, the recipient is Ksenia Kursanova from Penn State University. Ksenia displayed a remarkable initiative while serving as our first VFS Student Council president. The Student Council was brand new, so she had to hustle, and she showed us exceptional effort, support, and persistence in support to the Vertical Flight Society. She also serves as an officer of the VFS Penn State chapter, all while studying under the VLARCO there at Penn State. So in recognition of her contributions, she'll receive a $4,000 scholarship, as well as the Executive Director's Pin. that I've been wearing all year. So come on up on stage, Ksenia. Thank you. All right, so now I'm going to ask our chair, Harry Nahadas, up on stage, and he's going to announce the Nikolsky Lecture.
I'm very pleased to introduce this year's Nikolsky Lecturer, Sikorsky's Dr. Peter Lorber. Dr. Peter Lorber has had a distinguished 40-year career in rotorcraft aerodynamics with leadership roles at Sikorsky, a Lockheed Martin Company, and United Technologies Research Center prior to Sikorsky. He holds over 90 technical publications and 16 patents, with work widely cited in research and textbooks. A Vertical Flight Society Technical Fellow in 2010 and recipient of the Dr. Alexander Clemen Award in 2018. Dr. Lorber has also earned numerous awards from UTRC, Sikorsky, and NASA. After earning his PhD in aerodynamics from MIT in 1984, he led pioneering research in dynamic stall, flow control, and active rotor technologies. At Sikorsky, he contributed to major programs including the CH-53K, S-97 Raider, and JMR Defiant, with a focus on aerodynamic validation and interactional aerodynamics. He also played a key role in full-scale testing of high-speed rotorcraft and is currently supporting NASA's Dragonfly mission to Saturn's moon, Titan. In honor of these accomplishments and the lecture he is about to present, I would like to bestow on Dr. Lorber the Nikolsky Medallion. Dr. Lorber?
What I'm going to try and talk about this afternoon is how the experimental methods in general wind tunnel testing and analysis, including actual analysis and computational fluid dynamics, have had complementary roles over the past 40 years in developing rotorcraft aerodynamics. I'm going to do this by means of a series of examples and some sidebars on how the technologies in both areas have developed, what are the enabling technologies, and how, in some sense, things have circled back around. Okay. So the period I'm interested in is 1985 to 2025. What I'm going to, talk about are 5 categories: benchmark experiments, active flow control, production aircraft development testing, technology demonstrators, which are crucially different than a production aircraft development, and then finish up with activities that are more focused on CFD validation. For each of those areas, I'm going to try to describe the motivation and objectives, what are the experimental enabling technology, what was the state of analytical and computational analysis at that point, give a very, very brief example of some of the findings, some of the computational comparisons, and how that impacted on future developments. This is mostly chronological. It's not planned to be comprehensive, and primarily because of the ability to get it approved through our systems, it's focused primarily on things that I and my colleagues have been involved with that have been previously published, so we didn't need to go through an approval cycle that was too lengthy. Okay, the first topic is benchmark experiments, and the first one is oscillating airfoils and wings, which are seemingly simple geometries, but needed very significant amount of care to get to the appropriate answers. The motivations in this period, which was the mid-1980s, was threefold. Rotor blade dynamic stall, which is of interest to the helicopter community, fixed wing supermaneuverability, which was of interest to the Air Force at that period, and propeller stall flutter, which was of interest to, at that time, our partner company, Hamilton Standard. The idea, starting out on the upper right, was an 8-foot wide blade section sitting in the, at that time, UTRC wind tunnel,
we're trying to get to realistic Reynolds numbers in the millions and Mach numbers up to 0.6. The key experimental enabler at that point was the availability of compact, thermally stable pressure transducers that could be put into many different types of models, in this case, the wing. The second one was fully digital unsteady data acquisition system. It was immature at that point, but it was a great improvement over analog tapes. And also, in this case, the ability to use high-powered hydraulic systems to generate any waveform of pitching motion of this model that you wanted. The analytical state-of-the-art was relatively simple then, lots of semi-empirical models for dynamic stall. CFD was moving along, but still also relatively simple. And there are certainly many questions to be answered, especially as you went to the lower right picture, which was taking the same model, sweeping it, making it three-dimensional, worrying about tip effects. Typical experimental results were these type of many pages of black and white line plots that were published in that period in time. Color imaging was a luxury item that was expensive and complicated to do, and even more expensive if you wanted to publish it. So we were measuring pressure distributions, lift, moment, drag, laminar turbulent transition, effects of all the independent parameters. Contemporary work at that time was done at many places, including US Air Force Academy and NASA Ames. Computation early on in the 80s and the 90s was starting to be Navier-Stokes solution methods with relatively straightforward turbulence models. They didn't do a bad job here, they didn't do a great job. More recently, things have gotten much better. Higher resolution, improved separation, separated flow, transition. It's still a struggle for these full-scale conditions. Large eddy simulations in the 2017, 2022 have been done at an increasing Reynolds number, but it's still a challenge computationally to get the details of the flow proper at these high flight conditions. Okay. The second series of benchmark experiments were a model helicopter rotor. This was slightly later, in late 1980s to mid-1990s. The motivation was a multi-measurement comprehensive data set so that the analysts could combine blade air loads with far-field acoustics, blade air loads with bending, deflections of the blades. You wanted to expand the test envelope from relatively simple and safe conditions to high speed and thrust. You wanted to change the tip plan form. And as important, we wanted to be able to compare what was a UH-60A model rotor, about 10 feet in diameter, that we were testing with the full-scale airloads blade that Sikorsky was also producing, that NASA Ames and Army was going to be flight testing. Again, the enablers were the pressure transducers. In this case, we're able to put 176 onto this small rotor blade. Data acquisition was more mature, and you had composite rotor blades with repeatable structural properties and long life. And importantly, this was a partnership between the US Army, NASA, Sikorsky, and UTRC. So there was some money changing hands, but a lot of intellectual effort changing hands between all these partners over that period. Analytical state-of-the-art was, again, relatively simple: lifting line, prescribed wakes, comprehensive codes, beam models, 3D potential codes, starting to get to Navier-Stokes. Typical results, again: pressures, loads, blade bending, distortion, smoke visualization. You can see a smoke picture on the lower right. That was taken in the Sikorsky model hover facility, which is still in existence and still being used for testing. Contemporary work, the Ames NASA Army folks were doing things on a H1 rotor before that. There were other hover work being done at somewhat smaller scale at Maryland, Georgia Tech, other universities. And just to show that you can take data that was acquired before and make it in color. That was the surface pressure contours shown at the bottom of the slide. Then, excuse me, the same model was put into a wind tunnel. First, the German-Dutch wind tunnel in Holland in 1989. The rotor is this small thing up in the right before all of the microphones there. So it was a reasonably sized rotor in a very large anechoic wind tunnel to get the acoustics as well as the aerodynamics, measuring the same sorts of things. You then added some additional measurements when this experiment was extended 4 years later in the UTRC tunnel, getting wake positions from smoke visualization. The picture at the bottom was a picture of tip vortices coming from one part of the blade going back in, which actually was published in Vertiflight back in those days. And you're trying to get, obviously, what happens when you change all the parameters such as Mach number, thrust, tip shake. There were other DNW test campaigns that the Army and NASA did in collaboration with the other industry partners. And obviously, there was also a very large-scale complementary effort by NASA and the Army, taking the instrumented blades, doing flight testing in the 90s, and then going back and doing full-scale wind tunnel testing within the last 10 years. So this has been a long-term effort that's got a lot of benefits to the community. CFD comparisons, early on, it was trying to combine a little bit of data with a little bit of analysis. Prescribed wakes for hover, which was, I would call, fair correlation. Taking the measured pressures and adding acoustics was reasonable. Taking the measured aerodynamic loads and adding the dynamics analysis back in 1992 was fair. And going the other way, trying to model the whole thing again, was better but not great. More recently, this has all been vastly improved analytically using transition models, blade deflections, and interactions. This is the most recent work that was done in hover that did quite well. There are still some differences in there, and obviously this work is comparable to all of the improvements in modeling the H60 airloads rotor, similarly with the computational CFD, CSD methods of the last 15 to 20 years. Okay, the second major topic is active control. This was a very hot topic starting in the mid-1990s. Our involvement with it kind of covered a 15-year period until 2010. The idea was you wanted to find a way of breaking the paradigm of the passive rotor and improve noise, vibration, and performance. You wanted to develop the required actuators and control systems, and you wanted to try and identify system-level performance. Enablers were everything that was talked about before in terms of measurement techniques, but also adding the ability to make rapidly moving actuation and control systems. There was obviously a lot of work being done, excuse me, in academia from multiple of the people sitting here, Maryland, MIT, MDHC, and Boeing. ZFL in Germany was doing a lot of work on BO-105, 53G, IBC flight testing, and all of the Heart 2 activities. The other piece slightly later was NASA ZFL Sikorsky UH-60 IBC at NFAC, which was using the same blades that we had been built earlier on. So the analytical state of the art at the start of this period were component models for different pieces, an unsteady airfoil. Maybe you're starting to use some decent Navier-Stokes codes at that point, but the system models were really federated. You had a bunch of different models of different types that were kind of tied together. Typical experimental results. Type of one experiment was putting an active flap onto that same wing model that was developed before, getting pressures, air loads out to 0.8 Mach number, seeing what happens with your trailing edge flap when you're trying to do it during dynamic stall. There were a variety of individual blade control things being done at model scale and full scale with a hydraulic actuator, trying to get there. Again, is there a performance benefit? Can you reduce vibrations? Can you help acoustics in terms of BVI? And how well is all your actuation system doing in that point? Some lessons learned from all of this. The first one, which was not unique to us, is avoid hydraulic slip rings. Trying to get high-pressure hydraulic fluid into a rotating model without having a large bucket underneath it doesn't work very well. Try to avoid inserting complex systems into small legacy flight rotor blades. That also is much more complicated than it may seem at the time. Low-frequency noise measurements are challenging, even in very large wind tunnels. And the final lesson here is trying to separate relatively small aerodynamic performance benefits from the trim of the rotor is also a challenge. But it was very educational through the period, and there are many groups that are still working on these active control attempts, but again, it's somewhat in the past as far as we're concerned. The next active control piece is flow control. This was late 90s, 2004. The flavor that we were interested in was called directed synthetic jets. Again, you're trying to reduce drag, you're trying to avoid dynamic stall of your rotor blades, and you're trying to advance the technology to do that, the flow control actuator designs and the authorities. The basic idea of this method is in some way you have a jet of air coming out of your airfoil, going in and out. It's helping to energize the boundary layer over the airfoil, prevent it from separating. The enablers were all the previous aero measurement and control techniques. So you're seeing a theme here that every piece kind of builds on its predecessors. Another enabler was system design models for the actuators so that you could do a lot of analytical work with a reduced model early on, avoid too much experimental tinkering. And the other enabler in the later period was the ability to do CFD modeling of the coupled internal flow inside the actuator and the external flow. This was part of the DARPA micro-adaptive flow control program that was going on at the time. We were one of several teams working on that. There also were a lot of flow control activities going on at that time and continuing in academia. The analytical state of the art by the 2000 period, external flow CFD was quite mature, but these actuators were often modeled as a surface boundary condition. You were only later on being able to model the coupled system, which proved to be important in predicting the capabilities. So the slide here is showing some of the computational results. The red is the jet coming out of the actuator slot and then coming back in again at the other part of the cycle. As you can see, we're getting very detailed analytical measurements. You're able actually to start optimizing the design. But overall, the lessons learned was, yes, we were able to design actuators that had the authority that we needed to have, but in practice, at these realistic conditions, opening a slot hurts you before your actual flow control is able to help you, so that we were limited in the ability to meet the objectives for the higher Mach numbers that you would see on an actual rotor blade. So the final piece of this was a few years later in the 2012-2016 area, where we were trying to see what was the maximum ability you could get out of a flow control actuation for a rotor blade stall. The idea again was delaying stall and adding lift. This particular experiment, which was funded out of Susan Gorton at NASA, was to try and see what you could do up to a relatively high Mach number 0.5. So the enablers, again, were the measurement techniques, the hydraulic pitch mechanisms, all of the insight into dynamic stall and flow control that ourselves and other groups had obtained over the years. This was also using the model in the middle there, which was a 6-foot high oscillating wing that had been previously developed under the Vertical Lift Consortium project for the Glen Icing Tunnel. CFD modeling was doing very well here for the coupled flow. I skipped over one of the key enablers was the combustion-powered actuation technology from Georgia Tech, which was one of our partners across into here. So that was really, if you're pumping hydrogen and air into the model, igniting it with a spark, that's about the strongest non-nuclear actuation system that's available. So again, you're doing this related sorts of measurements, measuring the pressures and lift. We are adding particle image velocimetry there to get the flow field on the model. And the computation for the airfoil was what's called the CFL 3D code, slightly more sophisticated and accurate. The conclusions were, we could clearly see the effect on flow control. The effect was primarily after stall, so you didn't really succeed in increasing the lift over the airfoil. You did increase the average lift because you were better off after it had stalled. The CFD actually did well for design and capturing the trends. The issue became, when you're looking at trying to move this onto a rotor, delivering gaseous hydrogen through a slip ring from a shaft out to the blade and delivering it on a rotor blade would be seriously challenging, even harder, I think, than delivering hydraulic fluid, and obviously could potentially have very serious consequences if things leaked. Okay, so a sidebar, I mentioned PIV. The maturing of flow velocimetry over the past decade or so has been a very important addition to the experimental toolkit. The legacy was you would measure one location at a time with a hot wire or a laser Doppler velocimetry system. This required significant amount of test time, which is a significant amount of money. Early years of PIV in the mid-90s, it tended to be a local expert was required as a full-time activity to develop and operate it, but at that point, the resolution and the ability to go to a large distance was limited. In the middle years, such as in the previous experiment, capable systems were developed. It was mostly smaller scale, but it still tended to require a full-time expert to operate. More recently, near turnkey systems are available for an affordable cost, and they can generally be used by what I'm calling a part-time expert. We're able to get high quality and resolution and then export data to other users relatively quickly. The bottom is an example of that in a small wind tunnel that was added in and getting flow field behind a model. This is a steady image. You can do the same thing for unsteady. So that's been a significant technological improvement over the past, say, 20 years. Okay. So now we talk about production aircraft. Production aircraft development programs were historically probably the most important use of the wind tunnel for actual industrial users. The technology in developing it was largely empirical, based on prior programs, empirical relations, handbook drags, and certainly in the 70s into the 80s, the analytical methods were limited. So you really were required to get all of your data essentially used in the design and pre-flight out of the wind tunnel. You needed, for a development program, to have new technologies previously qualified. You weren't really trying to go into there with a new rotor blade. That had to be established in a prototype sense. You started out with a small-scale airframe, trying to get basic design characteristics, vary them around, then went on to a larger model, such as seen on the right here. And then in the 80s, you started adding powered rotor models to your fuselage as a matter of course. But through all of this, I think the flight test was still remaining the primary way to find system-level issues. So what did you do for a wind tunnel testing in a development program? The number one thing was, what are the forces and moments? What's the lift, the drag, the moments on the fuselage and on the rotor? You would like to know what are the loads on the blades. You'd like to know pressures in a few locations of interest. You might put some tufts on it to identify some of the basic flow field features. You added other things on a need and budget available basis, such as pressure measurements for interactions, flow-through or aspirated engine inlets, hub accelerations. Sometimes you added a powered tail rotor. You did dynamically scaled empennage. There was a period where Dynamics was also doing rotor testing to try and get optimizations. Customers, aerodynamics, handling qualities, loads, dynamics. I will mention, however, that derivative aircraft that didn't have significant new features, even in the earlier days, often were able to omit or reduce the quantity of wind tunnel testing. So over the last 20 years, there's been continuous improvement, but at a more rapid rate. In the CFD analysis of components has been grouped into larger and larger systems. You're currently in the position where you're generally able to simulate the full aircraft with tail rotors, main rotors, inlets, exhausts, internal flows, dynamics and structures, adding coupling between the rotors and the fuselage, both aerodynamically and structurally, and very recently, co-simulation putting the control systems in. The challenge remains to make it all happen quickly and reliably. And no, I'm not showing any CFD animations in this paper. There are plenty of other presentations out here for the next few days that you can see that. Okay. The next category in development of leading to an aircraft is technology demonstrators. They're different in the sense that a technology demonstrator is trying to prove some specific capability. It's not trying to get a unified aircraft that you're later going into mass production. So your analysis and experiment needs to focus on what's required for safe flight, what are you trying to demonstrate, and try and avoid unexpected results from flight test, or if you were not able to avoid the results and you get them, then you need to try and figure out what happened and how do you fix it. Some examples in our company have been the X2 technology demonstrator 2008, the Raider in 2010, and the rotor blown wing that is going on now from 2023 into 2025. I'm going to talk on the rest of this slide on the X2 technology demonstrator. That was what we call a rapid prototyping process. Analysis in the 2008 term for these configurations was kind of limited. There was no pre-flight wind tunnel testing done. The rotor design was made by one of my colleagues in the room, Dr. Bagai, using relatively simple methods plus deep aerodynamic insight. The fuselage was designed empirically, and it had a simple shape as shown in the upper right. Didn't have a lot to be analyzed. The hub fairing was based on prior wind tunnel tests from decades before, plus one small-scale non-spinning wind tunnel test, which was the effort of one of my other colleagues, Dr. Wake, sitting out here doing that. It was relatively simple, but it demonstrated that it should work. And the propeller blades were commercial off-the-shelf items. Post-flight, the rare thing had happened. The power required was less than anticipated. So in that case, people were willing to go through and actually build a wind tunnel model after the flight test was through, a fifth scale model to try and explain that. That was the model in the two lower pictures, airframe model to measure the drag and say, yes, the drag was about what is expected on the model. We had a propeller behind it and did that isolated and after the model, and that kind of identified that the boundary layer ingestion process, improving the propeller efficiency, was really what was causing the aircraft to fly somewhat better than expected. And that was something that was then incorporated into later designs. So it might have been nicer to have done the wind tunnel test before the flight test, but doing it afterward was still very informative. And the second half of this was the S-97 Raider development, which was a few years later in the 2010 to 15 process. Analytical tools were improving, but high-performance computing resources were still quite limited, and it was focused more on computationally analyzing one component at a time, using different tools for each of them. There was a series of wind tunnel tests conducted there on the airfoils, on the airframe, on the hubs, since the hubs are a high drag mechanism, and that was culminated in a 1/3 scale powered coaxial rotor and airframe model, which was a new test rig that was tested in several entries out at the NFAC at Ames. A few years later, when you got into flight test, at that point, considerable effort had been applied to improve the CFD-CSD tools. They were also available then to support flight test and develop fixes for issues with the aircraft, and then also for follow-on pieces. So you've moved along a little bit, doing a more co-equal collaboration between the computational methods and the experimental methods, and again, learning as you're going in both cases, and then applying that knowledge to the next iteration. Okay. The second sidebar is model fabrication. In the legacy period, small airframes were handcrafted from wood. The large airframes were, again, mostly handcrafted from fiberglass and metal and wood. Instrumentation was sparse. In the 2000s, CNC machining of metal structures was common. 3D printing started to appear. In fact, we were doing some of that in the late 90s. But the print volume of each piece was limited, the accuracy was limited, and the surface finish was limited. So there was still a significant amount of complex hand finishing required. Current state over the past few years, 3D printed OMLs is pretty standard. The instrumentation is located directly from the CAD design into the parts. The CAD goes from the vehicle design to the wind tunnel model to the CFD, so everything is consistent and able to be compared quite easily. However, there still is craftsmanship and skill required for the design and the fabrication. The slide images on the right are showing a wind tunnel Black Hawk model from the late 70s, a early 3D printed but hand assembled CH-53K model from the early 2000s, and then some fully 3D printed, very complex internal flow models from a few years ago. Okay. This topic is focused CFD validation. So this is something that's become more important over the past few years, when you're trying to do something to get some data set that can be directly used in CFD. This first example was somewhat accidental. The experiment was an add-on to a development program on, in this case, the S-92 in 2000. The motivation was rotor and airframe wakes on empennages was a concern. CFD models at that time were not mature enough, and there was very limited computational capability to practically address it. So the idea was to go through, make some detailed flow field measurements and surface pressure measurements on the model at the end of this particular development program entry. The enabler was there was a 3 velocity component traversing hot film system available from a previous program. The horizontal stabilizer on the aircraft had 40 unsteady pressure coulites into it. That's what the middle image is showing, the pressures on the upper surface of the horizontal stabilizer as the blade passes by. The data systems were more sophisticated there, so you could actually get a large data set in 1 week, which was an affordable activity, even though it was partially shared between Sikorsky and UTRC. Even Dr. Ken Rosen was willing to put up the money to do that. The data after that test was preserved, fortunately, and then 18 years later, the analytical capabilities had matured to the stage where we were able to go through and actually try and predict all of these fine details accurately. This was both the Helios tool and Star CCM Plus. The things that helped were improved turbulence modeling, fine spatial grids, fine time sets, and HPC capability to do that in days rather than weeks to months. And this also, obviously, everything requires interest, which means funding to demonstrate and refine the interactional aero computations. The lower right slide was an example of the measurements of the wake behind the rotor. There were several VFS papers in that period which compared that to the computational analysis, and generally it did quite well. The last example here was the most recent one, 2022 to 2024, focused on spinning coaxial hubs. The motivation was there was trying to understand the impact of the wake of the hubs and blades eventually into the empennage, into the propulsor. CFD maturity and HPC capacity was there to do this problem, but we still wanted to get some good validation data set. This took advantage of the 3-component PIV system that was available. It took advantage of high capacity pressure tap measurement techniques, and obviously very large, complex 3D printed components which were needed to do this in a reasonable amount of time. So this then took advantage of Helios' improved capabilities, and again, you're able to provide solutions in days. The video at the top is actually the PIV data showing the wakes coming off of the rotors and the hub. Red is free stream full velocity, yellow is reduced velocity, and blue is full wake pieces. So there were lots of comparisons between test and the CFD tools, and again, that was doing quite well, so we basically were able to conclude at this point that this was a solvable problem using the analytical methods. Okay, so why so little talk about data systems, since that's one of the things that I've spent a lot of time on over the decades. 40 years have produced a massive increase in the bandwidth, the processing speed, the capacity, the channels, the number of screens to show the data, the complexity. The upper picture was a PDP 1120 in 1981 at MIT, which was close to the state of the art for academic research at the time. You see you interacted with it with what was called a deck writer, which was a printing terminal. The lower one was 40 years later with a more complicated system that had many, many more channels, lots of displays, lots of computing, lots of recording of information tied to control systems, etc. But the principles really have remained the same. You really want to acquire what you need, not anymore because that just takes you more time and effort, but certainly not less. Know the conditions at each point. That's been an issue that's continued in many cases. If you have multiple systems, you get different answers, and how do you synchronize them? So you really want to have them all tied together. You want to have things simultaneous, and you monitor really only what's important in real time. We've had situations where, because I can monitor hundreds of parameters for safety of flight, then you have hundreds of parameters that can cause a false positive and get you concerned. So don't, again, acquire what you need, not more, not less, and certainly also understand your uncertainty. How accurate are your data? What contributes to it? And how does that feed into your correlation? Okay, starting to wrap up here. Some of the trends over time, obviously experimental computational capabilities and speed have increased. Experiment over this period has made detailed pressure and velocity measurements practical for increasingly complex systems, going from a simple two-dimensional wing to a full rotorcraft, both in the wind tunnel and flight test. Computation has expanded even more rapidly, pushing back many prior limitations on the models, the resolution, the complexity, again, enabled by HPC capability as shown in the charts below. So these are plotting in log scale versus time. On the left, the grid points going from millions to billions over this last 25 years, enabling full rotorcraft, full complicated rotorcraft to be simulated with the highest fidelity models. In the case, timing has also dropped. Again, a log scale. This is showing You know, how many CPUs per case, CPU per case versus time. So you have a few cases over a certain amount of time to thousands of cases over a certain amount of time. So your capabilities have gone up. However, there's still need to think about some things that haven't changed. You know, the focus areas have varied, started with benchmark experiments, simple geometries, focused on mechanical and flow control devices, all the way along was product development technology demonstrators, and a more recent focused on validation for complex systems for analysis, which in some sense is wrapping back around to the benchmark experiments of the earlier days. You want to take some configuration, accurately measure it, take what you need to take, and then compare it with what is your best physical understanding, either analytical or computational of it. Capabilities to produce data, both experimentally and computationally, have vastly expanded. New vehicles are more complex, and the models of them are also complex. There are, of course, because of that, more opportunities for unexpected issues to arise, and obviously more opportunities to optimize the system to get the best out of it. But I maintain there's still a continuing need for human intelligence in the middle of this, cross-checking both the multiple numerical models, the multiple physical models. It's always easier to find a problem if you have some idea that there's another person working on it with the same or better or different method getting that out. Thorough examination of the results. Do they make sense? Are they consistent? If they're not, dive into it and try and figure it out. If they do make sense, still dive into it and try and figure it out. So I think that is the end of what I had prepared to talk about today. I think we have time for a few questions.
All right, I get the first question. That's awesome. So very cool presentation. Thank you. You showed a lot of computational and experimental. And a lot of times, especially as students, we see kind of experimental versus computational. So I'd like you to kind of just share your thoughts on looking to the future, how we as engineers can make the most of both of these tools, computational and experiments, to do our jobs as best we can moving forward. Thank you.
Yeah, I think you clearly need to look at both of them. One of the things that was done in the early period that's experimentally that's not done at this point is using your model to generate massive databases of things. At that point, that was the only way, not only in rotorcraft, but also in missiles and fixed-wing aircraft. You have tended more to change from kind of a pure testing everything to a focused experiment to measure things that you either don't understand, that are new, or enough of it to provide touch points for the analysis to tie to. You may, though there still are some cases where you're taking thousands of different conditions, you can often get by and identify what are the few hundreds of good conditions that span the space of the experiment, of the physics, and I understand those well versus having to directly feed the output of the wind tunnel test data into your application.
That's a great talk, Peter. Thank you. You gave
By the way, you also used the PDP 1120
yes,
at the
I did.
time.
Which gets to my question, which is, you cited that interactional aerodynamic data that you sat on for, well, you saved for 18 years, something like that?
Yes.
How many data type reconfigurations or reformatting did you have to do in that process of archiving? Because I think that's something that, as you showed, the technology for the computational capability and data storage has migrated through many different cycles.
Yeah.
What did you have to do to make sure that you still had
That's a
that
very
data?
good question. There's kind of two pieces of it. One is it still available? Did you store it on something that you can no longer read it? Did it get deleted when person A, B, or C retired? It's easier now, at least your numbers are crossed there, but that was clearly an issue from the 90s on, that everything was a unique format. It was a tape or a zip drive or something or other that if you didn't change the format, you were lost. I think that's a little bit better if you're able to get it into some reasonably defined numerical setup, put it onto some shared drive that your organization is preserving. It doesn't guarantee that it's still not going to be there, but one of the issues in many of these things when we're going back and looking at it is in the earlier days, storage space was very expensive. So you did whatever you could to make your numbers as compact as possible, which ended up being binary storage, which tended to not like to go from one system to another and takes excessive amount of effort to go through and do that. But I think that's something that applies both to the computational and the experimental end, that think about how are you preserving both your data and your description of your methodology and what have you. Now it seems to be a lot of PowerPoint presentations on something that are sitting off in some area. The documentation and the archiving is a struggle, but if it's only one person who knows about it, that one person will not be there forever, and you need to be able to go back and pull it up, because we've had that one example for the flow field data. We've had other examples over the past year in trying to pull out Black Hawk experimental information from the 70s and the 80s that we didn't want to have to go back and try and measure again. And in some cases, it was well documented, and even if you had to scan in an old report with numbers into it, you could do that. In other cases, it disappeared. It was, oh yeah, this was such and such who did that, and he retired 10 years ago, and we have no idea what happened to any of his data. So that's another message that I should have thought of before Bob asked the question, but preserving it and documenting things and making sure there's more than one person who knows what's going on is very important.
Well, thank you, Dr. Lorber, for sharing your lifetime of work and support to the vertical flight community. Another round of applause for Dr. Lorber. Thank you so much. So now we will bestow the medal. We'll take a photo, and for those that have received the Nikolsky medal in the past, you'll come up on stage afterwards. We'll have a group photo. Thank you.